Welcome to qnawire.
This question is basically about derivatives. All you have to do is verify that the ground state wave function, psi100, satisfies Schrodinger's equation with an energy given by this expression. So all you have to do, mostly, is calculate the second derivative of the ground state wave function with respect to x, y, and z. So let's do it for x first. So deriving psi100 with respect to x is equals to square root of pi r0 cubed, which is just a constant factor with respect to x, times the derivative with respect to x of e to the minus r divided by r0. Then remember that the derivative of an exponential is equals to itself, so we just have e to minus r0 again. But now we have the derivative with respect to x of the exponent of that exponential. Again, the r0 term is constant with respect to x, and so is this minus 1 term here. And we got minus e minus r divided by r0 divided by r0 times the square root of pi r0 cubed times the derivative of r with respect to x. Remember that r is equal to x squared plus y squared plus z squared to 1/2. Then this derivative will result in the following. So this 1/2 factor from the exponent will drop. We have 1/2 here, and this will multiply the same expression elevated to 1/2 minus 1, which is minus 1/2. So we got this in the denominator. And now we have the derivative of the inside. So the derivative of x squared plus y squared plus z squared. As we are taking the derivative with respect to x, only the first term will be affected. And we get the derivative of x squared, which is 2 times x. These factors of 2 simplify, and we get minus e to minus r divided by r0 divided by r0 square root of pi r0 cubed times x over r. Now note that this factor here is just psi100, so this is equals to minus psi100 times x divided by r0 times r. Now we have to derivate again. Taking the second derivative with respect to x, we get the following. Using the product rule, we get the derivative of the first times the second plus the first times the derivative of the second. Note that r0 is constant with respect to x, and we got d over dx of x divided by r. Now we already know what is the result of this derivative. We have calculated it. So we get minus psi100 times x divided by r0 times r times, from this term, x divided by r0 times r plus psi100 divided by r0 times the derivative of x with respect to x, which is 1, divided by r plus x times the derivative of 1 over r with respect to x, which is the following: to d over dx of r to the minus 1. And then we get this is equals to minus psi 1, 0, 0, x squared divided by r0 squared, r squared, plus psi 1, 0, 0 divided by r0 times 1 over r plus x times. So this minus 1 factor drops from the exponent, and we get r to the minus 2. Then we have to multiply by the derivative of the inner factor, which is the derivative of r with respect to x. Then let this minus factor come inside to get psi 1, 0, 0, x squared divided by x0 times r squared, plus, not plus anymore, minus psi 1, 0, 0 divided by r0 times 1 over r minus x divided by r squared times dr over dx. dr over dx, as we had already seen, is equals to this term here. So it is equals to x over r. So we got it. Then, massaging this equation, we can write it as psi 1, 0, 0, x squared divided by r0, r squared, and well, this was r0 squared, I forgot to put it, minus psi 1, 0, 0 divided by r0 times r, plus psi 1, 0, 0 times x squared divided by r0 times r to the third. Finally, this is equals to psi 1, 0, 0 times x squared divided by r0 squared times r squared minus 1 divided by r0 times r plus x squared divided by r0 times r to the third. And this is with respect to x. The calculation for the other directions is just analogous, so we get d squared psi 1, 0, 0 dy squared is equals to psi 1, 0, 0 y squared r0 squared r squared minus 1 divided by r0 r plus y squared divided by r0 times r to the third. And finally, for the z direction, we get psi 1, 0, 0 z squared divided by r0 squared r squared minus 1 r0 r plus z squared divided by r0 r to the third. By summing these three terms, we get derivative of psi 1, 0, 0 with respect to x plus the second derivative with respect to y plus the second derivative with respect to z is equals to psi 1, 0, 0 times. Now we have x squared plus y squared plus z squared, which is r squared divided by r0 squared times r squared, plus again r squared divided by r0 r to the third minus 3 divided by r0 times r. And this can be written as simplifying r squared with r squared and this r to the second with this r to the third, 1 divided by r0 squared plus 1 divided by r0 r minus 3 divided by r0 r. We can further simplify it to get finally psi 1, 0, 0 1 divided by r0 squared minus 2 divided by r0 times r. Now, we can substitute this result in Schrodinger's equation, which is this one. Then, we have minus h bar squared divided by 2m times this term, which is equals to psi1 0 0 times 1 divided by r0 squared minus 2 divided by r0 times r, minus 1 divided by 4 pi epsilon 0 minus 1 divided by 4 pi epsilon 0 times e squared divided by r, e squared divided by r times psi1 0 0, and this is equals to E, the energy, which is given by this expression, so minus m e to the fourth minus m e to the fourth divided by 8 epsilon 0 squared h bar squared times psi1 0 0. So all these psi1 0 0 factors we will cancel out, and we should get that the left side is equals to the right side. So let us message the left side. Minus h bar squared divided by 2m r0 squared plus 2 h bar squared divided by 2m r0 times r. These two simplify with this one, minus e squared divided by 4 pi epsilon 0 times r is equals to minus m e to the fourth divided by 8 epsilon 0 squared h squared. Now remember that the Bohr radius r0 is given by epsilon 0 h squared divided by pi m e squared. Then, by substituting the Bohr radius in these expressions, we get minus h bar squared divided by 2m r0 squared. So epsilon 0 squared h to the fourth divided by pi squared e to the fourth m squared plus h bar squared divided by m epsilon 0 h squared divided by pi m e squared times r minus e squared divided by 4 pi epsilon 0 r, and this is equals to minus m e to the fourth divided by 8 epsilon 0 squared h squared. Now we can simplify a few things on these expressions. So this mass can simplify with that mass, and this mass with this mass. So now we have minus h bar squared times pi squared e to the fourth times m, and this is divided by 2 epsilon 0 squared h to the fourth plus pi e squared h bar squared divided by epsilon 0 h squared times r minus z squared divided by 4 pi epsilon 0 r, and this is equals to minus m e to the fourth 8 epsilon 0 squared h squared. Now remember that h bar is equals to h divided by 2 pi. Substituting this in this expression, we get minus h squared pi squared e squared m divided by 4 pi squared 2 epsilon 0 squared h to the 4th plus pi e squared h squared divided by 4 pi squared epsilon 0 h squared times r minus e squared divided by 4 pi epsilon 0 r. This is equals to minus m e to the 4th divided by 8 epsilon 0 squared h squared. Then we can simplify a few things again. So h bar squared with h bar squared, pi with pi, and here we can simplify h bar squared with h to the 4th, pi squared with pi squared, and that's it. Now we get minus e squared times m divided by, oh, dz is to the 4th. It came from this term. I just forgot to write it. So e to the 4th times m divided by 8 epsilon 0 squared h squared plus e squared divided by 4 pi epsilon 0 r minus e squared divided by 4 pi epsilon 0 r, and this should be equals to minus m e to the 4th divided by 8 epsilon 0 squared h squared. Note that this term cancels this term, and finally this term is exactly the same as this term. So Schrodinger's equations is satisfied.